Good afternoon. It's my great pleasure to introduce our speaker today. Pleasure and honor, William Will Chueh. Some of you may have seen, we were just talking about this, his TED Talk a couple of years ago. He was good then. He's even better now as a speaker presenting very technical subjects, which is not an easy thing to do. So Will Chueh is assistant professor in the Department of Material Science and Engineering, like Mike McGee was, who was our first technology speaker in the very first seminar this time, and a center fellow for the Precourt Institute for Energy. If I remember it right, you might have been the first center fellow.
That's right.
At the Precourt Institute for Energy.
Yes.
That is true. He did his BS, MS, and PhD at Caltech in material science, and then got a very prestigious Truman Fellowship at Sandia National Lab for 2 years. And then we were fortunate that he decided to come here to Stanford. So during his short but illustrious career, my view is he's won every award at the highest level award at every stage of his career. So keep that string going. And unlike what I did with Ren Orens, I'm actually going to read one sentence from his bio that I think captures the essence of Will Chueh. And that is, one grand challenge for materials used in lithium-ion batteries is to bridge the enormous span and length scales through the integration of theory, advanced characterization, and data analysis. I think a lot of people have thought about doing that, but very few people, in my view, have actually done that in a decisive and meaningful way. And just to demonstrate that, he's chosen as his talk today, Bridging the Enormous Span of Length Scales in Lithium-ion Batteries. Will, take it away.
Thank you very much for the great introduction, and I think the expectation couldn't be any higher, so thank you for that.
But you're still smiling.
Well, I'm trying to. So thank you for coming to the talk. So I gave this seminar 4 years ago when I started at Stanford. So it's great to come back to the same seminar series and present some of our latest results. So lithium-ion battery is one of these very hot topics today, but I'm going to try to remove some of the heat from the topic and give you some substance behind it and lay out some of the challenges that we face today. So as introduced, I'm a material scientist. I'm also a Precourt Fellow, so I'm trying to have a wide span of views on these problems. And I'm also associate with the SLAC National Accelerator Lab, and you'll see that there's a lot of characterization involved. So maybe just to sum up our overall activity in the research group, we're about 25 graduate students and postdoctoral scholars, focusing on really merging bottom-up and top-down approaches to accelerate the development of technologies to enhance mobility and to increase the penetration of renewables in our energy system. The way we approach the problem is both fundamental and applied, and you can see this in just the list of our funding sources, ranging from the basic sciences to industrial funding. Just to give a context of the type of problems we work on, this is just one example of a carbon neutral energy cycle, starting with sun. You can start with wind, geothermal, and so forth, and ending all the way to utilization in terms of electricity. And you can see that there are many steps involved, for example, in the capture through solar cell, photoelectrochemical devices, storage in terms of batteries, fuel cells, hydrogen, delivery, and ultimately utilization, and how do you close the loop by converting the product back again. So our work span all of these activities, but today I'm going to talk about what is really exciting for us in the past 5 years, which is to develop a fundamental understanding of storage technology and apply it to solve real-world problems. So undoubtedly, all of you have heard about lithium-ion batteries. If you have not, this is probably the simplest explanation I can give for it. It is really just two reservoirs of lithium, one which is higher in energy, one is lower in energy. So you can think of this as the analog of the hydroelectric dam. So you're just flowing water from up to lower elevation, generate electricity in the process. But this is very, very small, and really all we're doing is shuttling lithium between the two reservoirs repeatedly. So flowing down, pump up, flowing down, pump up. And we'll want to do this for many thousands or tens of thousands of times. Applications range from big, such as electric vehicles, to small, such as the Internet of Things, sensors, and so forth. Over the past 2 decades, we really have seen a tremendous scaling up of lithium-ion batteries beyond anyone's imagination. So even just 5 years ago, lithium-ion battery technology wasn't the benchmark as far as cost is concerned, but today it is. Any storage technology now has to compete with lithium-ion batteries. And you can see this in the dollar per kilowatt hour. Just in 2005, we went all the way from sort of the $1,000 to $2,000 range per kilowatt hour to today, which is now approaching $200 per kilowatt hour. And this is at the cell level. And we are expecting to see further improvement down the road. Of course, going from 2,000 to 200, maybe not too bad, but going from 200 and down, it gets increasingly more difficult. And today's talk will highlight some of the basic science as well as the application challenges that we need to address. And how do we go about developing an all-inclusive approach toward addressing the problem. And just very briefly, the reason why lithium-ion battery is difficult to develop is that the number of times you can recharge them, also known as the cyclability, as well as the energy density, so this is how far you can drive your electric vehicle, for example, they don't have the best relationship. So typically, things that cycle very well don't have a very high energy density, and things that cycle extremely poorly have very high energy density. And what you really want to do is to approach the internal combustion engines and other fuel-based technologies, such as fuel cells, which you have both. But with the lithium-ion battery is really going in the wrong direction. So today I will also talk about how we can move up to this quadrant where we have both life and energy density that is required for applications. So one of the grand challenges associated with developing lithium-ion battery technologies is the large span of length and timescales involved. And this is just an example going from what you might recognize as a cylindrical lithium-ion battery. This is typically in the amp-hour level. Then if you zoom in, you can see the internal jelly roll. So this is kind of the sushi that makes up the lithium-ion battery. If you zoom in further, you go to the porous electrode. These were individual agglomerates of particles are stacked, forming the positive and the negative electrode with the electrolyte in between. If you zoom into one of those particles, these are called agglomerates, and they themselves contain thousands of individual particles. And this goes from amp hours to picoamp hours. So here we're talking already 12 orders of magnitude in terms of the energy scale. And then we can go smaller down to the atomic scale, of course, looking at electron, redox process, ions, and so forth. So the way we've been approaching this problem is to develop a combined theoretical, experimental, and data analytics approach to merging all of these length scale. And then here I also show the time scale. So here we have the atomistic process at the angstrom level and picosecond, moving up to the single particle, typically at the seconds level and microns, all the way to the device level, and involving, for example, degradation at many, many years, and then scales of centimeters, tens of centimeters, and so forth. Let me just list a couple of the tools we use to frame the problem. For example, at the smallest length scale, we use things like spectroscopy, X-ray scattering, diffraction to figure out where the atoms are sitting, the electronic structures of the material. Then at the single particle level, we use microscopy. Bigger things, we use tomography to do three-dimensional imaging. And then for the full battery system, we cycle them and then obtain their electrochemical performance. Analogous to this experimental method, we also have a set of modeling, simulation, and data analytics method to match up. For example, we have quantum mechanical calculations, molecular dynamic calculation, phase field, macro continuum simulations, circuit models, and so forth. And what we're doing is to basically merge everything between theory, experiments, and data, and then try to go across this entire diagonal of time and length scale. Now, much of the work I will present are done by a team of more than 20 students and postdoc present and past. These are their pictures, so please note that their placement on this particular plot is not related with their time to completing their PhD, although this one might be particularly tantalizing. The work was also enabled by many terrific collaborations within the Stanford community and also beyond. I'll just point out a few whose work will be highlighted today. For example, Mike Toney at the Stanford Synchrotron Radiation Light Source, David Pendergast at Lawrence Berkeley National Lab, Martin Bazant at MIT, Edwin Gassier at Purdue, and also Richard Bratt at MIT. So we have formed a really nice nucleus of people to try to combine all of these things together. So let's get started. First, let me present the lowest of the length and time scales at the atomistic level. So the question I want to talk about here is how can we actually connect understanding at the atomic level to the thing that's happening at the highest level of the electrochemical cycling, okay? So let me give an example of how do we think about approaching the theoretical capacity of the positive electrode. So this is one part of the battery in which the energy of lithium is the lowest, okay? Sometimes people call this the cathode. And this is just a plot showing the theoretical and the practical capacity, energy density of various material. On the left, you have lithium cobalt oxide, so perhaps folks are familiar with them and their use in consumer electronics, all the way to more recent material set. So you can see the blue, which is the practical, is far lower than what is theoretically possible. And one of the main challenges is the fact that the oxygen tends to come off these materials. These are typically metal oxides, lithium cobalt oxide, nickel cobalt manganese oxide, lanthanum manganese oxide, lithium iron phosphate, so on and so forth. And they also suffer from the other issue that you can't put a lot of lithium per host. So you can think about a hydroelectric dam scenario. What you want to do is to be able to drain the dam all the way to the bottom. But if you have to have a huge amount of hosts to hold the material, then your energy density goes down. So what I will talk about today is really a success story in the past decade that was initiated from Oregon National Lab. It turns out that if you put a lot of lithium, more than what is stoichiometrically possible in these material, you get a huge increase in the energy density. You can see, in fact, you can almost double that of lithium cobalt oxide just by stuffing it with excess lithium. So let me demonstrate this schematically. This is just an atomistic picture of the crystal structure. You can see that there are oxygen layers, transition metal layers, and lithium layers. So this is the standard stoichiometric material. But when you start replacing some of the transition metal with the lithium, so you can now notice I replaced 1/3 of the transition metal with lithium. So I've now just increased the energy density considerably by about 33%. And it turns out that by doing so, the material actually becomes more stable against oxygen loss. So what happens is you get this huge capacity gain, almost increasing that of lithium cobalt oxide by 70%, and you don't have the same problem as lithium cobalt oxide, which is losing oxygen, floating away, and causing irreversible damage to the battery. What is really strange about this material is the first time you charge the battery, it undergoes a very strange activation process. And when you discharge it back, the voltage profile is entirely different. So this material has some sort of odd transformation on the first cycle that no one really truly understands what's going on. So our goal is to try to understand why replacing some of the transition metal with lithium, which increases the capacity, can actually further stabilize the material and enable high capacity cycling. So I will just present you the final result in the interest of time. What we found is that the redox chemistry, okay, so what is happening with adding and removing an electron, is strongly connected to the structure dynamics. So it turns out the material actually undergoes a small change in the local structure at the atomistic level, which then gives the special property so that the oxygen doesn't float away. This is a standard material, so when you remove all of the lithium from that layer I showed you earlier, what you can see is you have these oxygen that is connected to the transition metal from the top view, but it turns out that this is not the complete picture. What happens is when you start removing so many lithium from the material, some of the transition metal actually hops down to the lithium side because they're very similar in size. This is known as the transition metal migration. And when you migrate this transition metal, the consequence is you start forming these dangling oxygen bonds, okay? Because now the transition metal migrates down. You can see it from the side view and the top view, there are several of these dangling oxygen. And these dangling oxygen has particular properties. These are density functional theory calculations showing what happens when you move that transition metal down into the lithium layer. You actually start shifting electronic state associated with the oxygen to much higher energy here. And this is actually one of the main reasons why the oxygen doesn't come off, is because you create these dangling oxygen bonds and the electrons like to stay there, and it allows you to cycle the battery without losing the oxygen. So of course, this is a theoretical picture. We've now performed experiments here at SLAC showing that this transition metal migration coupled with these dangling oxygen is indeed responsible. This is a cycling profile of the battery. The second plot here shows you those special dangling oxygen. And then in green here, this is a diffraction signature of those transition metal migrating into the lithium side. So you can see the special dangling oxygen and the transition metal that has migrated into the lithium layer is completely mirroring one another. And this gives us the direct proof that the two are indeed connected. So the standard picture that the structure is very static, lithium-ion battery, is completely not accurate. And in fact, the structure actually changes as you charge it and discharge it. So to understand the origin of stabilizing these high-capacity cathodes, you need to understand the connection between the two. And this is just to show you here, we can also spectroscopically see this oxygen state. This little dot here, we are among the first to have discovered it. We can actually see being directly connected to the cyclability of the battery. So the lesson here is that the structure dynamics, this ability for the transition metal to move around and replace the lithium side, can enable you to have very high lithium to host ratio without the oxygen loss. So this was a really nice story around how atomistic level understanding can help you engineer higher capacity, more stable battery. So now let's move up the length scale. Now we're going from the atoms to the particles. So now this is one individual crystallite. So you can think of this as a single crystal, typically on order of a few microns in size or a few hundred nanometers. And we're combining here experimental microscopy method to see how the lithium is getting in and out with phase field simulation to model the process. So now I'm going to turn the material from the layer oxide, so that's the analog of lithium cobalt oxide, to another related chemistry, lithium iron phosphate. So this is commonly found in your power electronics tools. If you have a battery-powered drill or a vacuum, very likely you have lithium iron phosphate. This material has a very specific behavior, which is it either likes to be lithium-rich or lithium-poor. So it doesn't like to be in between. This is known in material science as phase separation. Okay, so it's either full of lithium or empty of lithium and nothing in between. And if we take a picture of this and we map out where the lithium is sitting, we can actually see this lithium-rich and lithium-poor phase. So lithium-rich is in red here, lithium-poor is in green. So if you charge the battery to 50%, so this is half lithium, it phase separates like oil and water into this lithium-rich and lithium-poor domain. You can see the color difference here. This is collected by X-ray microscopy at the single particle level. And what is very important about these phase boundaries, so where the green and the red meets, is an area of extremely high stress. So here we're talking about on the order of 2,000 psi at the interface. So as the battery is cycling, whenever you develop this sharp compositional gradient, this is accompanied by stress that will lead to the failure of the particle. So over time, the particle essentially fractures. Okay? However, it doesn't actually happen. These batteries are extremely long-lasting. You can charge them for tens of thousands of times. So what is happening in this material that make it not fracture? So that was a question that we set out to answer in 2012. It took us 5 years to fully answer the question. It turns out there's a lot of great science behind it. What I'm going to show you now is a set of movies. One movie is when I charge and discharge the battery very slowly, so it's behaving very close to the equilibrium. This is the first movie. Here we are putting in lithium at a rate that is done in 5 hours. So this is called sort of a slow charge. You can see, just like the previous set of pictures, the lithium boundary forms and progresses from the outside to the inside of the particle, and this is collected in situ using X-rays. But now, if you take a look at the compositional profile, so this is just looking at the color distribution as a function of position, you can see it's either full of lithium, so X being 1, or it contains no lithium, so X being 0. So this is just a validation of thermodynamical property of this material, and everywhere in between is forbidden. So you have no composition occupying the forbidden part of the thermodynamics phase diagram. So this is good. But when we now started to put in lithium at a much faster rate, so now this is turning from 300 or so minutes down to 30 minutes. So this is now 10x faster. And then let me now play the movie. You can see, rather than forming these sharp phase boundary, which is accompanied by a very large mechanical stress, the phase boundaries are gone. In fact, what you're seeing here is the color stepping through red, yellow, and green. which means we're actually accessing these thermodynamically forbidden states. So this was very unusual to us. Why doesn't the battery behave as it should according to thermodynamics? And it turns out it has everything to do with the kinetics of the battery. The standard theory around this was just a matter of the time scale. Folks thought, well, maybe the time it takes to form the phase boundary is much longer than the cycling time of the battery, so therefore you don't form it. So that's the picture of the 30-minute. It turns out there's quite a bit more, and we can actually analyze those movies carefully to extract the details. So let me show you the result. This is the free energy curve of the battery, so let me take a deep dive just for 2 minutes if you'll permit me. This type of curve will give you phase separation because it's unstable. It has a non-monotonic shape, and it goes down as you increase the amount of lithium, so the material just wants to be lithium-rich or lithium-poor. Of course, this is just the equilibrium picture. If you now think about the kinetics, so if you have to put in lithium, you have to put in a little bit more voltage to overcome whatever resistance occurs at the interface. And this, you can take a look at, is a typical resistance as a function of composition. The thing about batteries is it doesn't behave like a normal electrochemical material because the composition changes. Okay? Every time you put lithium in, the lithium content changes. And as the lithium content changes, its resistance changes. So this is just a simple model saying the battery is the most efficient at taking lithium halfway. So when it's half filled, it has the lowest resistance. So now what you can do is you can take the current and you multiply that by the resistance, and you add it to the open circuit voltage. When you do that, you get something like this. This is the resulting voltage curve under cycling. And you can see this downward bending curve maintains the same shape. And this is because the resistance is very high for having no lithium, the resistance is very high for having a lot of lithium, and the resistance is almost zero when it's half filled. So this means that if you look at the yellow part here, which is the amount of extra IR voltage you have to put in, it's almost zero in the middle and it's very large near the end members. So this means that the voltage curve will be tilted even more so the material still undergoes a phase transformation because it's unstable. But now, imagine you take a different shape. So rather than having the resistance being the lowest at half filling, imagine it is the lowest at quarter filling. So how does this alter the yellow shaded region on the right? Well, it turns out it changes the shape entirely because now the resistance is very, very low initially, which means the yellow region will be very thin as you put in current, and at the end member composition, then the resistance becomes very large. Having this particular shape of a profile for the resistance then allows you to bend the shape of the potential profile. So rather than having it go up and down, it just goes up monotonically. And in material science, this is known as a non-phase separating system, which means if I put in some composition here, the system will not want to undergo the phase separation into that lithium-rich and the lithium-poor regions. And it turns out experimentally, this is exactly what we saw. We measured from those movies I showed you previously, the resistance is a function of the amount of lithium inside. And we showed that at about lithium 0.2 out of 1, the resistance is the lowest. And this allows you to basically bend the shape of the voltage profile, therefore turning the system from a phase separating one into a non-phase separating one. And the reason we don't want phase separation is we don't want those boundary, which has enormous stress associated with it, to fracture the particles. So we actually now have a very good explanation why these particles cycle so well despite undergoing this huge multiple thousand PSI boundaries between the two phases. So if we take the same material and zoom out a bit, it turns out more interesting physics await. This is now looking at many of those particles. We're zooming out by about a factor of 100. Each one of these dots you're seeing are individual particles. So now we are taking a movie as the battery is cycling. And we naively think, well, all of the particles will just behave the same, right? Not really. A battery is full of heterogeneity, and in this case, it couldn't be more so. It turns out that as you charge the battery, only very few number of the battery is actually charging at a time. So you think you're charging the battery over 1 hour, but really you're charging one individual particle over just a matter of 3 minutes because the amount of active particle is actually just on the order of a few percent. So this is very interesting to us. So as we discharge a particle, you can see the so-called particle by particle motion. So this is very strange to us as well. If you look at a higher resolution image, you can actually see most of the particle is either full of lithium or having no lithium. And very, very few is in an intermediate state of lithium, and those are the actively discharging particles. So the question is, why does this occur? So now let me show you an animation which is informed by our phase field simulation performed in collaboration with our colleagues at MIT to show you what happens when the rate is very, very low, so we're charging the battery very slowly, or when the rate is very, very high, so we're charging in 15 minutes, for example, which is what you might want to do in your electric vehicle next time you go to Safeway and try to charge up during your shopping trip. So this is what happens when you charge a battery very slowly. It looks something like a popcorn, which means the amount of active particle is very small at a given time. Okay, very few percent of the battery is active. And this is what happens at a low rate. But when you go to a very high rate, so now you're trying to charge the battery much faster, you actually get the counterintuitive picture that the intercalation occurs much more uniformly. Okay, so we have a picture in which you have a very heterogeneous process at low rate and very homogeneous process at high rate. This is entirely counterintuitive. Normally, you would think if you crank up the rate, the system will become more heterogeneous. It turns out there's a simple explanation for this too, using the classical concept of nucleation and growth in material science. It turns out this system is actually limited not by the rate you can fill the particle with the lithium, but the rate it takes to start it. Okay? So when you are at a low rate, you're barely activating the particle, so very few of them are active. But at a high rate, you're applying such a large driving force, so the nucleation rate is occurring much faster. So let me draw an analog to standard material science. This is looking at the solidification of iron. So we're starting with the iron liquid. This is looking at, the solidification of iron. Blue here is liquid iron, and the red is solid iron. So this is just precipitating out. Normally, what you will see is you will get a few of these nucleation spots, so the solid iron forms, and they keep on growing, growing, growing until they collide and until the entire thing turns into solid iron. So this is what happens in a medium in which the iron can move around freely between the two phases. But in a battery system, this can't happen because the batteries are consisting of individual isolated particles directly from one another. So you have these phenomena occurring in each individual particle. They're getting activated. But once the activation propagates to fill the entire particle, it stops. Okay? So when this particle is full, you need another event for another particle to start nucleating. So the rate of this nucleation actually determines how many of the particles are active. So when you're cycling your battery very slowly, you're applying only a very small driving force, so your nucleation rate is very low. So this is what happens when you charge a battery slowly. When you charge a battery faster, then the nucleation rate gets higher. So at some point, every individual particle has one of these events, and then the battery becomes more uniform. So this is perhaps quite a bit counterintuitive. And we were able to assemble all these knowledge about this material, lithium iron phosphate, and actually provide the engineers with a phase diagram. Not just a static phase diagram, a dynamic phase diagram, looking at the effect of the rate at which you charge the battery, looking at the kinetic property, the resistance, looking at diffusion coefficients, and we can actually map out where you want to be in order to get a very uniform battery. So the most uniform regime here is on the upper right. This is where every single particle is active, and also every single particle does not undergo phase separation. And that is the dream situation. We want batteries to be in this regime so we don't have any hotspots. We don't have any stress or fracture induced by compositional gradients. But a lot of the time, the battery actually operates in this regime, which is the worst. This is when only very few particles are active, giving you the hotspots, and then each of those particles further undergoes phase separation. These stripes represents the movie I showed you where those high stress occurs at the interface. So this is good at the single particle level, but we're not done yet. So let's now move up. One more length scale, so now coming from the microns to the tenths of microns. And here we're using three-dimensional tomography, much like the CT you use in medicine, and then combining that with microcontinuum simulation to figure out what's happening when you start putting a lot of these particles in contact with one another. So one of the most direct thing happens when you put the particles in contact is mechanical coupling. So when one particle expands a little bit, the other particle feels it. And so this introduces a lot of coupling at this sort of tenths of micron level. And let me now impress you with a fly-through of one of these particles. This is a two-dimensional cut of the tomography result for this layer oxide. So this is very similar to the particle, the chemistry I reported in the atomistic study. And you can see it has individual particles, it has pores inside. So the movie basically shows you a fly-through of the particle through one of those pores. This is where the electrolyte could get in. This is where the lithium salt would get in. This is also where the electron would come in contact with the particle. So, although it is impressive to look at, what information can we actually extract? One of the main themes of the talk today is how do we turn cool results into actionable engineering concept to get us better batteries? And that's exactly what I'm going to show you next, is taking this really cool exotic movie, which is collected right here at SLAC. In fact, it was collected about 4 years ago, okay? But only very recently has the mathematical tools allow us to reconstruct the image with such high fidelity to see inside through this roller coaster ride. So now let me go through the science. So now we have the structure of the material. What we wanted to understand was how does stress couple to the degradation? In the same way that we're looking at the single particle level, we're now looking at exactly the same phenomena at the agglomerate level. So now we're talking about 1,000 or so particles piled together, forming these so-called secondary or agglomerate particles. One thing that really surprised us was if we took this battery material, we charged it to a certain state, and we let it sit for hundreds to thousands of hours, you would imagine that the battery will be very uniform by then. All the kinetics is gone, there are no more current in the battery, it is just sitting there at its happy equilibrium state. We took an image, so this is a 2D projection of the 3D result I showed you earlier, and the color had the same meaning as previous, which is the amount of lithium. We were expecting to see more or less a yellow particle because we parked the lithium composition right in the middle, but it turns out that was not the case. We saw that even after waiting hundreds to thousands of hours, the heterogeneity persisted. And in fact, it's very significant because this is a 2D integrated projection. That means what you're seeing here is even more pronounced if you look at the 3D version. You can see, for example, near the interior of the particle, there are part of the particle that is less charged and part of the particle that's more charged. Why is this a problem? Well, as I mentioned earlier, when you have different amount of lithium, you have mechanical stress. But it turns out there's one more problem with it. There is a coupling between the voltage locally and the mechanical stress. When you have a different mechanical stress state, you have a different voltage. If you have a different voltage, a different open circuit potential, what happens is those are going to be the spots that get charged first. Okay? In fact, you get this pattern because the system is trying to maintain a constant potential. So the way we do it, just like a balloon, if you squeeze a balloon, the air goes somewhere else. Okay? That's exactly what you're seeing here. You squeeze part of the balloon, the lithium goes somewhere else. And this gives a very interesting coupling. At the atomistic level, this material expands when you put lithium in one direction and shrinks in the other. So when you put different particles of variable orientation and you throw in some of these porosity in there, like what I'm showing you, you get a very interesting stress distribution inside. And this stress distribution is giving you this variation in lithium content, which reflects the fact that the open circuit potential is different in different part of the particle, and you can see that by relaxing the particle. So let me show you some of the simulation result from my colleague, Edwin Garcia at Purdue. So he has taken basically model structure, and he has thrown in pores and different crystals in it to see what happens. So this is the simplest case when you only have a single crystal, okay? So imagine taking a single crystal very big and you drill a couple holes in it. So we can't do this experimentally, so we do it in the computer. So this is where you're seeing a single big grain with the same orientation, and you have pores inside. And these are the calculated stress in the system. You can see basically near the pores, you have a buildup of the stress and the release of the stress around the edge of the particle. And now, if we start to look at the crystallographic effect. So now imagine we have many, many individual grains, but no pores. So now the colors represent the orientation of the grains, the crystal. So remember, these crystals expand anisotropically. So it expands in one direction, shrinks in the other. As you put lithium, then you also get a very interesting distribution of strength, owing from the fact that some particles are expanding this way, some of the particles are expanding this way, others are shrinking this way. And when you put the two together, you get this very complex pattern of the stress distribution. So this is having both the pores and the different crystals, and you can generate the stress pattern. And we're now in the process of comparing this theoretical result to what we measure experimentally. Again, the reason why this is important is ideally, we want a battery particle which has uniform lithium concentration. And what we're showing you here, because of this mechanical effect at the atomistic level, when you put a lot of particles together, you can actually develop a lot of these stress gradients. Over time, the particles will fracture, they will fall off, and the battery will lose capacity. And this is one of the main failure mechanisms as you increase energy density. In fact, this is one of the biggest challenge associated with lithium-ion battery technology today. So now we come to the final part of the talk. So now we are moving upward in length scale. Now we're going to go to the highest, which is at the level of a single battery cell. The standard approach here is to take experimental results, so I'm charging, discharging the battery thousands of times, recording the capacity each time, and then I'm going to model it using circuit models, equivalent circuit, try to understand the degradation. The challenge here is that the actual degradation process in a real cell is so complex. In fact, you can see just marching from the bottom up, there's so many different things, and we don't even know how they connect one to another, the degradation process. So this is very top-down. One of our recent activity is to think about, well, why don't we let the data tell us what to do? In battery cycling, you accumulate quite a bit of data, at least for a material scientist. And what we're doing here is to replace the circuit models with a data-driven model. So no a priori knowledge of the system, just seeing what the data tells us. So this we call a data-driven optimization and modeling approach. And I'm going to talk about three particular problems we hope to impact. And this is now really zooming out from the atomistic level to the particles to the agglomerate I showed earlier. We're hoping to enable fast charging. So how do you charge a battery in 15 minutes while still have a cycle life of 3,000? Formation cycling, one of the most expensive steps in manufacturing a battery, other than the material cost, is the idling time it takes in the factory. So we have to break in these batteries in a specific way. This is known as a formation cycling process. And from our colleagues at industry, this constitutes about 50% of the cost of the manufacturing process. The third, which is very important as we start thinking about second use application for batteries, so when the batteries come out of a used electric vehicle car, how do we know it's good? So state of health indicators are also very important to diagnose the battery, even if you don't know the history. The common challenge in all these three problems is the large dimensional space involved in the parameter set. Each one of these problems involve 5, 10, 15 different parameters. And very quickly, you go out of control. Well, in fact, the computer just went out of control. Let's see here. Let's see here. That was not planned. Okay, let's see here. Okay, so let's do some simple arithmetic here. If you have 5 parameters you're trying to optimize, you look at 10 values for each of those parameters. You cycle 10 batteries for each one, and you cycle each battery 1,000 times. Okay? You add up the numbers and multiply them. This equals 1 billion battery cycles. So in order to optimize 5 parameters and going through 10 values per parameter require you to cycle batteries 1 billion times. So this is close to being an intractable number, especially considering the rapid development to market timescale for battery, which is around 3 years. Okay? So by the time you go through this process, the next generation battery is upon us. So what is the solution? Let's not touch it. So whatever works, we stick to it. The fast charging, if it works, we stick to it. The formation it works, we stick to it. So the challenge we're facing right now is, can we speed up this process? Can we use data and our knowledge of batteries to help cut down the time it takes to optimize fast charging, optimize formation cycling, and discover state of health indicator? So I'll show you, this is very preliminary, and this is a collaboration with Stefano Armand in computer science. We actually met at one of these Precourt dinners. It was a lovely event and led to this particular proposal, which was funded by Precourt, and also with Richard Bratz at MIT. The idea we have is to use a integrated testing and analysis system. So we want to basically test batteries, many thousands of them, each one of them in a different part of the parameter space. So we don't just want to test one parameter space, one value 1,000 times. We want to test each one just once. So each of those batteries are being tested at a specific way. So this allows us to access the large parameter space. The data comes out, okay? We don't wait until the battery fails. We discover what's called an early prediction algorithm, so we can try to see maybe just the first few tenths of cycle whether the battery will live or die, okay, for a given parameter. That early prediction then goes back into optimal experimental design. So for the battery that's going to fail, that's discarded. Let's throw that parameter space out. If we understand what the parameter space looks like, then we can adapt the experiment so we don't keep cycling the battery the same way. We keep honing in on the optimal way to do it. So you can think about fast charging. If you charge them in a certain way, the battery dies. We throw that part of the parameter space out. To us, this is a great way to basically reduce the number of experiments needed to find the optimal solution. So today, I'll just show you some of our results in the early prediction. This is really a success story of data science coming together with material science. What we have done here is taken about 100 or so batteries, and we charged and discharged them many thousands of times, giving a data that is about 100 million data points total. Okay, so it's a pretty sparse data set, but for material scientists, we're pretty happy. We don't deal with 100 million much of the times. And these are just some of the representations, and of course, these are the folks involved. That's Nick, Peter, and Norman. So they build this octopus look-like machine that allow us to charge the battery all under different conditions. The experiment data we get is, for example, the capacity versus cycle number. So this is the standard degradation curve. The voltage profile of the battery. So for each battery being tested, each cycle, you get thousands of data points in terms of voltage. And then you also get things like temperature. So these 100 million plus data points are then fed into an algorithm, and then to answer the simple question we have. From the few tens of cycles of battery cycling, can we predict how many times it will last? So what is the goal here? The goal here is, rather than testing the battery 3,000 times, let me just test it 100 times, and then I can stop the test. That will effectively increase my optimization rate by 30x. And that's exactly what was achieved here. We developed an early prediction model. We trained a very simple regression model with all the data we have. We picked out 5 features using a supervised approach. This was done by Kristen Servison at MIT. These include the capacity, some of the features you saw in the previous plot. I won't get into the details. I'll just share the results. This is the prediction versus observed. X-axis here is through the large parameter space that we were exploring, we got batteries to behave badly, so we can get maybe just 400 cycles out of it, all the way up to 2,500 cycles. And then we basically regress all of this data, and we found a very strong correlation by having some weighted component of each one of these features, and we're able to predict the battery lifetime from 400 all the way out to 2,500. So this is a very big set of data, very large parameter space, very different behavior of the battery. So when I talk to people from the auto industry, I remind them this is basically the same as test driving your car in real road conditions. So if I take my electric vehicle and drive it up and down Sand Hill Road, I'm not going to get very much excursion in the parameter space. But when I drive it around the country or around the world, I can span the type of behavior I see. And that's what we're doing here. We're spanning the battery lifetime by driving each battery differently, and then the resulting data set can be used to correlate this. The y-axis here is predicted only from the first 100 cycle. So if you give me the first 100 cycle, in fact, if you give me just the 100th cycle and the second cycle, just those two, give me the voltage profile, and I can tell you exactly how long the battery will last. So in terms of optimization, I no longer have to test the really good battery out to 3,000. I don't even have to test the bad battery out to 500. I will know its lifetime, and I can adjust my experimental design to save me time. We've shown that this not only extends to the previous chemistry, which is lithium iron phosphate graphite. This is from a battery manufacturer. We've also shown that it can work for other chemistry as well. Here, the data set is a bit smaller, so the scatter is worse. But overall, we're able to get about a 10% error from our prediction of lifetime. And this is good enough for us, because now when coupled with the optimal experimental design, we're able to speed up the discovery of the optimal process necessary to achieve rapid charging, short formation cycle, and even in this case, state of health predictions. So let me now wrap up with my final slide. Here we have the grand challenge of understanding and controlling the transport of lithium from the atomistic level from picosecond all the way to degradation over years involving battery cells and battery packs. Our outlook could not be more challenging. It is to seamlessly integrate these experiments, advanced characterization, data analytics across all of these length scales to achieve predictive and data-driven design of lithium-ion batteries. What I've shown you today is just an early glimpse. We're not really connecting them yet. Okay? We're doing basically research at each length scale. The goal for the next 5 to 10 years is, can we connect them? Can there be a single model that incorporates all the data all the way from cycling to the simulation, from the spectroscopy all the way up to the tomography, and then create an all-descriptive model of lithium-ion battery degradation and manufacturing and performance? So that is the goal we are trying to achieve. So with that, I'd like to again thank all the students, postdocs, and collaborators being involved, and thank you very much for your attention.
We have a few minutes for questions. Any questions? There was a lot to absorb right here.
Oh, for the battery cycling data, are you collecting any data other than electrochemical data, like temperature or anything, or strictly electrochemical?
Yeah, so far, we are collecting electrochemical plus temperature.
Okay.
But looking forward, we can measure things like stress. We can put a strain gauge on the cell, so that can measure the expansion of the cell, which is another indicator. We can put not one, but multiple temperature probes into each battery. And there may be other things we can record as well. So in data science, this is called data stream. So the more stream of data we have, the faster and more accurately we can describe the entire battery system.
You guys do. Go ahead.
Two things. Are you aware of the UCLA work over the last few years where they have graphene, layered graphene, and they charge and recharge a million times easily with no degradation?
Yes.
So the question then would be, why we want to store electrons and retrieve electrons, not ions. So why are we still dealing with ions, which have all these other issues, mechanical at that scale?
Right. So these sometimes so-called pseudo-capacitive behaviors, so it works more like a capacitor. So the storage mechanism is interfacial. Battery, the storage mechanism is bulk. That's why you need to get the lithium in and out. That's why it expands. In the pseudo-capacitive application, you're just relying on interfacial storage mechanism. That's why you can cycle them many times. Very much similar to capacitor we use today. The problem is energy density. So the power density can be extraordinary, okay? Because you can take the whatever ion or electron out very, very quickly. But the energy density tends to be a problem. And because the surface area is so high, you have other parasitic reactions that could also cause degradation in the system. So I think it's a balance. For the lithium iron phosphate I'm showing, those batteries can now be cycled also in seconds. So you're trying to blur the line between the capacitive application versus the bulk storage. So they have their own merits. The mechanism is very different, I would say. One, you need very high surface area. The other, not as high surface area.
Right, but that's the point. You have a smaller volume because then you're dealing with a carbon matrix. Right. That's not a complex massive ions. And the other point that I'm trying to bring up here is that fast charging chemically is not the same as filling. gasoline. Battery swap is closest to that.
Yep.
So your fast charging, how will that ever approach the speed of going to Costco and filling your tank of gas?
It's going to be a very challenging exercise, not because of the battery, because of the charger. So if you're talking about delivering, say, 100 kilowatt hour of energy in 2-3 minutes, okay, I don't want to be next to that charger when that process takes place.
10,000 volts at 1,000 amps.
So I think the DOE target is 15 minutes. Going beyond 15 minutes, I think is very, very challenging. The battery swap is great, but it comes back to another policy issue. Well, how do you know the battery's any good? When I go exchange battery in and out, who pays for that? So there's some very interesting material science questions.
Let's move on.
I'm wondering if you can get any more information by using short charging pulses with some relaxation time and getting down to the time where your various scales occur.
In fact, that's exactly what we're doing today. By having these short pulses either in a time domain or in a frequency domain, you can actually extract all the out-of-phase component from the response, because if you just wait, you're only getting the in-phase component. But when you get an out-of-phase component, you can start thinking about, well, what is the resistance, what is the time scale of that relaxation? And many of the experiments we're doing is this sort of relaxation experiment. You bring it to a certain state and you wait, and the way it relaxes teaches you a lot about the health of the battery. So we use this, for example, a frequency domain method called AC impedance spectroscopy. So just putting a sine wave of small perturbation and you're seeing the out-of-phase component, so that can give you the more capacitive response of the system. And that is a great way to, for example, add to the data stream we have. So rather than just looking at the steady state response in the DC, we can also look at the time domain response or the AC response of the system. So that's a great way to get more out of the system information-wise.
Looks like we have time for one more question. John.
Go to the last slide, if you would. So this is sort of reminiscent of the sort of model hierarchies that people used in, say, microprocessor design. So I'm curious, do you have a chart like this that sort of says what programs you use at these different levels, and where are there gaps where you wish you could connect them up, and what are the impediments that you're seeing in those? Did you have something like that for the data science?
Yeah, so at the atomistic level, the quantum mechanical calculations are well established. MD is fine. Phase field and up, these are basically mathematical equations we're solving, so you don't need any particularly powerful solver. The problem is just defining the equations that's involved, and importantly, knowing what the parameters are. So we are beginning to see commercial software that goes after this. For example, there's a software called Battery Studio that goes after modeling this process. I would say probably the chief problem contrasting microprocessors or integrated circuits and this is the number of materials involved. So in the IC business, we have a number of materials. And they swap over a decade or two. Batteries, they swap over every 2 to 3 years. So by the time that the time it takes to develop all these fundamental understanding is enormous. So I would also say that we need more resources to develop these understanding. Otherwise, the standard approach is just go to the top down. Let's just make something, if it works, it works. But then we won't understand maybe the more random or stochastic failure mode that, for example, lies behind many of these high-profile safety incidents. So I think these are some of the issues we're facing. It's just that fundamental investigation is not matching the speed of the materials development, and this is why we introduce a top-down approach, looking at the data instead, to see if we can speed it up so then we can actually catch up with the actual development time of batteries.
Good. At this point, let's thank Will one last time.
Thanks for inviting me.
Sure.